All right, let's take a look at our second example. So this is problem 1.3 from the text. So at 0.01 degrees C and 611.73 Pascal, water coexists in three phases: liquid, solid, ice, and vapor. Calculate the mean thermal velocity in each of the three phases in meters per second, kilometers per hour, and miles per hour. Okay, cool. All right, so here we're going to get an idea of how fast our molecules actually moving around us. And the first thing I want to kind of point out is, so we're asked to calculate the mean thermal velocity. And so what's important is remember that kinetic energy. Okay, so when we talk about kinetic energy of our fluid, right, the kinetic energy of our molecules in our system is only a function of temperature. All right. So temperature is a measure of the kinetic energy of the molecules in our system. All right, so kinetic energy is a function of T. So in this problem, when we're told that we have water at its triple point, so we have a liquid in equilibrium with a solid and equilibrium with the vapor phase. At phase coexistence, all of our phases are at the same temperature. Okay, so all of our phases will be at the same temperature, so the mean kinetic energy, all right, or in this case, the mean thermal velocity of the molecules in each of those phases will be exactly the same. All right, so there's only one calculation that's necessary here because, right, all three phases are at the same T. Cool. So now in terms of calculating the mean thermal velocity, so the pressure is not significant, right? That just tells us, or this is just meant to tell us that we have three-phase coexistence. Okay, so my temperature is 0.01 degrees C, okay, and what I'm asked to calculate is the mean thermal velocity. So how am I going to get that? Okay, so I'm going to scroll over to our text, and so here's my marked up version of the text. And what I'm looking at is the section on the Maxwell-Boltzmann distribution. All right, so this gives us our probability distribution of observing a molecule with a given velocity. And from that, right, here we have our expression for the mean velocity within our system. Okay, so the mean thermal velocity, okay, V bar, is given as 8 kBt over pi m, okay, raised to the 1/2 power. Okay, and we'll simplify this animal in a second. Okay, so first thing is Kb is my molecular gas constant. Okay, so we know R, right, my molar gas constant, right, when I think in terms of SI units, right, it has units of joules per mole Kelvin. Okay, Kb, okay, so this is my molar gas constant, is my molecular gas constant, and so it has units of joules per K in SI units. Okay, so this is my molecular gas constant, this is my molar gas constant. All right, so R is equivalent to, if I can get it right, Kb times N Avogadro, right? Where N Avogadro has units of inverse mole, right? Molecules per mole. Okay, so R and Kb are related, right? That relationship, or the constant of proportionality between the two of them, is just Avogadro's number. Okay, so first thing I'm going to do is I'm going to plug that in, okay, just to simplify it, okay, because I remember R, I don't remember Kb. So this becomes 8, so Kb, I'm going to replace with R over N Avo. So this would be RT over pi times N Avogadro times mass, okay, to the 1/2. All right, so now the next step is, okay, M, all right, my mass. So this is the mass of a molecule, okay. N Avogadro is, has units of molecules per mole. Okay. So M is the mass of a molecule, and Avogadro is the number of molecules per mole. Okay, so question is, can we relate this to molecular weight? Right? So my molecular weight, right, is equal to the mass, right, per mole. Okay. And so M, right? So M here has units of mass per molecule. Okay. And then AVO, right? Usually we just, give it the units as inverse mole, right? But essentially it's molecules per mole. Okay. So if I have N AVO times mass, all right? So if I have N AVO times mass, okay, that's the mass, per molecule, okay, that essentially gives us units of, so this would be molecules per mole, mass per molecule, mass per mole, right, which is equivalent to molecular weight. Okay. So as I simplify this, I'm going to rewrite this as V bar is equal to ART, okay, divided by pi times my molecular weight raised to the 1/2. Okay. And as I do this, I'll just need to keep track of units. So normally we think of molecular weight, it's grams per mole. Okay. Here, if I'm thinking of everything in SI units, mass would have units of kilograms. Right. And so, if I think about mass, so if I'm going to work exclusively in SI units, right, and that mass is in kilograms, well, my molecular weight's grams per mole, right? So I'll end up with divide by, say, 1,000. Okay, so I'm not going to explicitly write it in here. When we start to write out the units, right, we'll see it all come together. Okay. So the first thing I'm going to do is I'm going to simplify my equation, right, as such. All right, so now to collect everything we need, okay, whoop, come on. Didn't mean to open up a spreadsheet. Okay, so now to put it all together with everything we know, okay, R is my molar gas constant. Okay, so the value in SI units is 8.314 joules per mole Kelvin. Okay, now temperature. Okay, so temperature we're going to want in absolute units. So the value we're given is 0.01 degrees C. Okay, now remember our conversion factor. Okay, so if I go up to our scanned appendix, which we looked at in problem 1, okay, so we know that to convert from, it should be on here, to convert from Celsius to, all right, so here we go, that relationship between molecular weight. So my temperature in kelvins, my temperature in degrees C, plus 273.15. Okay. So 273.15, so that'd be 273.16 Kelvin. Molecular weight of water. Okay, so again, water will be in my appendix. All right, so molecular weight's essentially 18. Okay, so here, molecular mass or molar mass, molecular weight, we're given 18.015. Okay, that's grams per mole. Okay, if I'm going to stick with everything in SI units, right? So I know I have joules per mole Kelvin. Here's Kelvin. Right, and SI units be advantageous because then I know my velocity will be in units of meters per second. Okay, so if I wanted this in kilograms per mole, then I just divide by 1,000. Okay, and so I'm just going to write it as 18.015 times 10 to the negative 3, right, equivalent to dividing by 1,000 kilograms per mole. Okay, that way I have it in SI units. So putting it together, okay, all right, so I'm going to come over here. Okay, and we'll call this part 1. So R is 8.314 8.314. My temperature in Kelvin was 273.16. Okay. Then once easy enough, I'm not worried about the conversion factor here. Our molecular weight, (18.015). E to the -3, and that's kilograms per mole. Okay, so then to calculate my velocity, v bar, okay, it's 8 RT divided by pi times my molecular weight raised to the 1/2 power. Okay, so if I run that, okay, let's press that output. My velocity in meters per second is 566.5868. Okay, so this is all in SI units. So that's 566.5866. 566 .5868 meters per second. Okay, so that's pretty fast. 566.5868 meters per second. Okay, so that gives us our answer in meters per second. But then they also ask for kilometers per hour and miles per hour. Okay, so let's do it. So we have meters per second. To get kilometers per hour, we need a couple of conversion factors. Okay, so the first one I need is just a kilometer is a kilometer, right? So it's my SI prefix of 1,000. So I know that 1,000 meters is equal to 1 kilometer. And then here I have seconds. It's asking for a unit of time of hour. Okay, so I know that 60 seconds is equal to 1 minute. And then I know 60 minutes is equal to 1 hour. All right. And if I wanted to combine them, all right, 60 times 60 is 3,600. So I know I have 3,600 seconds per hour. Okay. All right, so if I want V bar, okay, in units of kilometers per hour, okay, and I could fully write this out. It's not a big difference. But if I have my velocity here in meters per second, let me start by converting meters to kilometer. So there's 1,000 meters per kilometer. So meters cancel. And then I want to get to hours. So if I take this in 2 parts, so I have 60 seconds per 1 minute. So seconds cancel. And then I have 60 minutes per hour. Okay, cool. So my velocity then is equal to, so if I come back over here, so again, I'm putting it over here, all right, so it makes me a little slower, but this way I can provide that MATLAB script to you and you can completely reproduce exactly what we have. So first factor would be kilometers to meters. Okay, that's just 1,000. And then we had minutes to second. So that was 60. And then we had hours to minute, and that was also equal to 60. Okay, so for part, Okay, so part 1, right, this original one is meters per second. So then part 1, to get kilometers per hour. Come on, to get kilometers per hour, I'll call this V bar 2. So it's going to be R, velocity in meters per second, okay, divided by kilometers to meters, okay, times minute to second times hour to minute. So in kilometers per hour, all right, that's really large, all right, 2.0397 times 10 to the 3, all right, yeah, so it'd be 2.0397 times 10 to the 3, right, so 2,000 kilometers per hour. So I guess it's a very good thing that the molecules don't weigh very much at all. So 2.0397 times 10 to the 3 kilometers per hour. And then the last part, we're asked for miles per hour. Okay, so to get miles per hour, we'll need one more conversion factor. So I go back to our scanned appendix. And let's see, the length. So if they don't have miles, then I'll have to Google it, as I don't know what that conversion factor is off the top of my head. Right? And so here's, R and KB if you wanted it up here. All right, so let me open up a new window, and I'm going to convert kilometers to miles. And so 1 mile, so actually let's see if we can't go in reverse. So so let's go from 1 mile to a kilometer. Okay. So we have that 1 mile is equal to 1.60934. 1.60934, and that's kilometers. Okay, so if I want my velocity in miles per hour, I'll take my velocity in kilometers per hour, 2.0397 times 10 to the 3, and that is kilometers per hour. And I will multiply by my conversion factor, so I have 1 mile per 1.60934 kilometers. Okay, so come back over here. So part 1 in miles per hour, my conversion factor of, so 1 mile is, so call it miles to kilometer. And that's 1.60934. So then V bar, call it 3. Come on. Gets a little touchy with my pad in front of me. So that's going to be equal to V bar 2, okay, divided by miles to kilometer. So miles per hour, we're at 1.2674 times 10 to the 3 miles per hour. 1.2674 times 10 to the 3. All right, so those molecules are really going fast. And so it's a great fortune they don't weigh very much at all. Otherwise, they might hurt. Okay, cool. So the velocity of the mean velocity of a water molecule at the triple point is 567 meters per second, which translates to over 1,000 miles per hour. All right, so the molecules in water are flying. Now B, calculate the mean translational kinetic energy contained in 1 kilogram of ice, 1 kilogram of water, and 1 kilogram of water vapor. So again, kinetic energy is only a function of temperature. So we only need to do this calculation once because the mean kinetic energy of all three phases will be the same since they're at exactly the same temperature. We'll go to our Maxwell-Boltzmann note, figure out our equation for kinetic energy. That'll allow us to calculate molar kinetic energy, and then we'll translate that to an extensive kinetic energy because we're told that we have 1 kilogram of sample here. Okay, so to get started, okay, so for B, okay, so for my physics class, I remember that kinetic energy is equal to 1/2 mv squared. Okay, so how we'll write it here in the context of Maxwell-Boltzmann would be my mean kinetic energy, so my expectation value of my kinetic energy is equal to the expectation of 1/2 mv squared, okay, where 1/2 and m, the mass of my molecules, all right, those are going to be constant. So this will be 1/2 m, then the expectation value of v squared, or I'll just write it as 1/2 m v squared bar. Okay, so now if I go to my notes here, so here's my expression for v bar squared. All right, so it's important it's v bar squared and not v squared. Okay. So v bar squared, all right, the equation they give us is 3 kBt over m. Okay, so the equation they give us is v bar squared is equal to 3 kBt over m. All right, and we're going to make the same substitution as we did up here. So effectively, go up, kBt over m just becomes r over molecular weight. All right, so kBt over m we showed just becomes r over molecular weight. Okay, so I'm going to rewrite this as 3RT divided by molecular weight. Okay, cool. All right, so let's compute this. Or actually, do I want to do that? Because I have 1/2 m, m would cancel, which would be pretty nice, and then I'd just be left with kb. Yeah, so actually, let me do that. I take it back. I'm not going to replace kb over m with r over molecular weight because when I go to calculate my kinetic energy, okay, which is 1/2 m v bar squared, that'll be equal to 1/2, okay, then m will cancel with that m, and so I'll be left with 3/2 kBt. All right, because 1/2 m, all right, m is going to cancel with the m in the denominator, so I'm just left with 3/2 kBt. Okay, cool. So let's compute it, right? So the mean kinetic energy is only a function of temperature. All right, this is cool. The mean kinetic energy is only a function of temperature. It's independent of mass. All right, so my mean kinetic energy then, okay, is equal to 3/2. Okay, so now I need to look up kb. Okay, so I'll write it down here as an aside. So I go up to my appendix, so close this conversion. All right, kb is 1.38 times 10 to the negative 23. 1.38 10 to the negative 23. That's joules per Kelvin. Okay, so this is 3/2. And yeah, so times kb, which would be 1.38 times 10 to the negative 23 joules per Kelvin. Okay, and then that's times T, which is our 273.16 Kelvin. Okay, now what's important here is Kelvin would cancel, and it appeared that I'm left with just units of joules. Okay, but technically it's going to be joules per molecule, right? Our Kb is our molecular gas constant. Remember, the relationship between R and Kb is N Avogadro. Right? N Avogadro, typically we just write it as having units of inverse mole, but it's really molecules per mole. Okay, so the kinetic energy that we're going to calculate here, okay, is really going to be in units of joules per molecule. Okay, so my kinetic energy, okay, is going to be equal to so if I start with the first part 2, so Kb, we had 1.38 e to the negative 23. And that's joules per Kelvin. So Ke is going to be equal to 3/2 times Kb times my temperature in Kelvin. Okay, so that's going to be 5.6544 times 10 to the negative 21, and that's going to be joules per molecule. All right, now how do I deal with this? Well, okay, first, all right, remember molecular weight. So my molecular weight of water, right, was 18.015, and that's grams per mole. Okay. Or equivalently, 18.015 times 10 to the negative 3 kilograms per mole. Okay. Then N Avogadro, okay, which is 6.022 times 10 to the 23. Okay, so the units, right, are always reported as just inverse mole, right, because mole is an SI unit, right? Molecule is not an SI unit, right? So what this really corresponds to is molecules per mole. Okay. So I can combine molecular weight and Avogadro to get the mass per molecule. Okay. So let's first do that. So N Avogadro, all right, so if I just go through the thought exercise, if I have molecular weight divided by N Avogadro, okay, that's going to give me units of kilogram per molecule. Okay. So if I take my kinetic energy, okay, if I write this out. So first what I'm going to do is I'm going to get this on a per mass basis. I'm going to get joules per kilogram. So I write this out as 5.6544 times 10 to the negative 21. That's joules per molecule. Okay. Then I work on my conversion factors. So first I use Avogadro's to get rid of molecule in favor of mole. Okay. So I multiply by N Avogadro. All right, and you see we're already getting closer to an order 1 number, negative 21 times 10 to the 23. So this is molecules per mole. And then in terms of molecular weight, its molecular weight is kilograms per mole. So I'm going to divide by molecular weight. So this is 18.015, okay, kilograms. Okay, actually I'm going to write it as just 18 just so I can fit it in here. Kilograms per 18 times 10 to the negative 3 kilograms per mole. All right, so moles cancel, molecules cancel, and I'll be left with joules per kilogram. Okay, so my kinetic energy. Okay, so this is my answer in joules per molecule. So get in joules per kilogram. I'm going to take my kinetic energy. Okay, let me add an additional constant, an Avogadro. So Avogadro's number is 6.022 e to the 23. So my kinetic energy in joules per kilogram is my kinetic energy in joules per molecule. I multiply by an Avogadro, and I divide by my molecular weight, right, which I already have here in kilograms per mole. So that's 1.8901. So 1.8901 times 10 to the 5, and that's going to be joules per kilogram. And since we're asked and a per, or how much, or the kinetic energy in 1 kilogram, we would multiply by that 1 kilogram sample, and we'd be left with our kinetic energy. Our mean kinetic energy is this 1.8901 times 10 to the 5 joules, right? And if you wanted to convert to kilojoules, you could. You would just divide by 1,000. Okay, I'm just going to leave it as such here. Okay, if I wanted to convert it to kilojoules, all right, it'd be my value divided by 1,000. All right, since kilojoule is just my 1,000 prefix. So equivalently, and I'd write this as 189.01 kilojoules. Okay, cool. And so I don't need to do it for all three phases. All three phases are at the same temperature. And then for the last part, okay, that's the mean translational kinetic energy. And then C, calculate the mean translational kinetic energy of an oxygen molecule at 0.013 degrees C and 1 bar. So actually, I don't actually need to do anything, because in B, okay, the first thing we did is we calculated the kinetic energy per molecule, okay, and we found that that was equal to 3/2 kBt. So it's only a function of temperature. Mass and pressure don't factor in at all. So the kinetic energy for part C, for that molecule of oxygen, would be exactly as we calculated here. All right, so this would be the value for C2. Okay, because when it comes to oxygen, right, mass doesn't influence this equation, nor does pressure. So since it's at the same temperature, right, it would have the same mean kinetic energy. All right, so that's exercise 2, or example problem 2. Hopefully that helps, and hopefully it makes sense.